JavaScript programs, and the speaker will be Saba Alamedadi.
Ah, yes. Yeah. Okay, so hello again. I'm Saba. I'm a postdoc at Northeastern here in Boston. And this is a joint work with Dijong and Frank Tip from Northeastern and Magnus Madsen from Aarhus. So I'll be talking about finding broken promises in asynchronous JavaScript. JavaScript is the most popular programming language today. And the reason for that is that it provides a particular set of features that make creating these modern and interactive web applications that are very popular these days very easy. However, JavaScript is single-threaded. So in order to have a lot of those features enabled, you would have to have asynchronous execution, like Maria mentioned. So in order to have responsive UIs, in order to be able to communicate between the client and server, have non-blocking I/O, all those stuff, you need to do asynchronous programming. And Maria very well mentioned how you would use callbacks and asynchrony in the context of JavaScript. And it's widely used in majority of programs. However, it comes at a cost. You can have cases like this that you would have levels of nesting between callbacks. And this is known as the callback hell problem. This is a very famous term in the community. So it's very easy to get lost within this pyramid. And this is not easy to understand, and it's definitely not easy to debug. Just following the flow of execution doesn't come intuitive to us as developers. So to help with this, more recently, promises were introduced into JavaScript. The concept is not new, but it's been only recently adopted into JavaScript. So the idea was that to help with the issues of callbacks, but still have the advantages of asynchrony. So more precisely, we wanted to have more linear structure for the execution, so it was easier for us to follow. We wanted to have better error handling to help with the debugging, and so on. So promises are basically objects that represent the eventual completion or failure of an asynchronous operation and its outcome. So you can create a promise object by using the promise constructor, which takes a generator function. So the generator function basically takes two callbacks as input, the resolve function and the reject. So basically what you're doing here is that you're performing some sort of an asynchronous operation here, and you want to decide the fate of that asynchronous operation and provide its output back to whoever requested this. So you do your operation. If it's successful, you call the resolve function, and you provide for it the outcome of the operation. If you have a failure, you call the reject function, and you provide the reason, which is usually an exception. So this is how you create a promise. And then you can start chaining these promises by defining reactions on them. So whether this promise is resolved or rejected, it can trigger another functionality in the code. So in this case, we use the then function to create a callback that handles when the promise is fulfilled successfully. And as a result, this then will create another promise, which you can, again, use to chain and continue this process, right? So I can define another then on this. And to the then function, you can also pass another callback to handle rejection. So in case your first promise is rejected, then the reject handler, the reject reaction will be called. And this, again, will return a promise. So you can see how they're kind of keeping up with that sort of more linear execution. And also, they wanted to provide better ways of error handling. So you have the rejection reaction, and also you can have a catch at the end of the chain to catch any exceptions that were escaping your chain. So a promise is just an object. When created, the status is pending. It could be fulfilled or resolved. In that case, it's settled. And it can only settle once. Once it's settled, the status will not change. And then the chain of reactions will be active. So this is an example of how you would use promises in real world. This is from GitHub, and this is just a check function that wants to check if a port is available or not so you can start your server on that port. So this is an asynchronous operation. So what this function does is that it returns a promise for you, which you can register a reaction on, right? So you see the ordering does not matter. You can register this reaction anytime. Once the result is ready, it will call your function. So in this function, basically what the programmer is doing is checking if the port is in use. It prints an error message and exits. If the port is available, it will print that the server is starting and actually starts the server. Nice, right? However, on the repository for this example, users were reporting a lot of random issues. So they're saying sometimes my server just prints that it's starting to work, but then nothing happens. There's no exceptions, no error messages. It just is not working sometimes. So the developers went and looked into this issue. So the thing that was happening was that because promises define their own way of exception handling, which is not the native way of JavaScript, exceptions are actually used to reject promises. So you can deliberately throw an exception to reject a promise in addition to directly rejecting it, right? But what if you have an exception that you did not anticipate? And a lot of exceptions happen in JavaScript in that way. So in that case, the exception will be used to reject the promise. So basically, the promise will eat your exception, and you will see no trace of it outside. So to fix this, the developers just the pull request just added a cache to just like basically catch this exception, and they were actually just rethrowing it, hoping for somebody else to catch it. But at least the exception was visible. So if you look online on GitHub, Stack Overflow, everywhere, there's a lot of confusion. And there are a lot of issues that happen that actually follow kind of similar trends. So promises were meant to help us. However, they still have a lot of issues. To help with these issues, we proposed an approach called PromiseKeeper, for keeping your promises, of course, which basically tries to help developers understand the execution for promise-based code and also find potential misuses of promises that could lead to such errors. So we have a dynamic analysis. Basically, we start by instrumenting the application automatically, which allows us to collect a trace of execution. What we do after is that from that dynamic information, we infer a set of promise graphs. So promise graphs were proposed actually last year in the same conference, and they're proposed to provide more formal semantics into promises and also provide this data structure that is meant to help you understand execution and help you debug the promise-based code. So for example, the graphs are just your usual graphs. Our nodes can be any object that's related to promises. So promises, values that are used to resolve or reject them, functions that are registered as the reactions, and a couple of other types of node that we'll get to. But basically, here you have a promise that's immediately resolved, and you see the value node resolving the promise node. You can register reactions for the promise. So what happens after that is resolved? You register function foo as the fulfill reaction or resolve reaction for that promise, which is invoked when your promise is resolved. In this case, we are not registering a reject reaction, so we just like put a placeholder, a default reaction, and we'll get back to the importance of that later. So your reaction can return a value, and that's important because the then function, if you remember, creates its own promise. So that value will be used to resolve P2, and then you're working on your chain. So you can see how for a little bit of code, this structure tends to grow a little bit, and there's more to it than it actually appears. You can also return a promise instead of a value, start linking your promises. There are all these sorts of semantics related with promises. And you can also use other promises to decide the fate of a promise. So in this case, this is just a sample API call, but you're waiting on P4 and P5 in order to resolve, to have the results for P1. So you have a bunch of these relations, and the details are in the paper, and I encourage you to look. Okay, so we analyze the code. We infer these graphs. The next step, we want to actually use these graphs to find out those anti-patterns in the code. And anti-patterns are common coding practices that are not necessarily but often correlated with with errors. Sorry. So they just make your code more error prone, even if they don't cause an error instantly. So we wanted to detect these misuses of promises in promise-based code. And we have a set of anti-patterns discussed in the paper. But as an example, remember the default reaction that was not, the reject reaction that was not registered. And this is actually the same problem that happened in our real-world example. They were not expecting the promise to be rejected, but it was rejected with an exception. But they had no way to support it. So basically, this is a very common pattern that you don't just think about errors when you think you're writing perfect code. And as a result, the whole chain might be affected. Another issue that can happen here is that my two promises at the top were never fulfilled or rejected. They remain pending. Sorry. As a result, none of their reactions were ever triggered. So any part of the code that depended on those promises logically will be dead code, and you'll just lose that part of execution. So these are just a couple of examples of the anti-patterns that we detect, but we have more. So what we do at this step is that we have the graphs. We find these anti-patterns. We want to actually give them to developers. We want to provide the reports of these anti-patterns along with the actual graphs that we visualize. And then we overlay those visualized graphs with warning notes so they could also visually find the points of interest in the graph as well. So this is a real graph coming from one of our subject applications from GitHub. And basically, you can see that you can follow the flow of execution. You can see what happened during the execution. You can focus on specific nodes and see, for example, here you had a promise that would resolve with a value. It had a fulfill reaction, which returned the value, which resolved another promise, which was linked to something else. So you can kind of have this side by side with your code and kind of make sense of what exactly happened during runtime. OK, so we proposed this approach. We actually created a tool that's open source, and our artifact is also available. But is it actually useful? We wanted to see if it actually helps developers understand promise-based code and find issues in realistic settings better. Is it helping us? So we searched on GitHub for Node.js projects that actually came with test suites. And the reason was that we wanted to programmatically execute these applications by running their test suites and and intercepting their execution. So we picked 12 Node applications from GitHub, and overall we had over 115,000 lines of JavaScript code, for which we ran PromiseKeeper and we got the graphs. So to just give you an overview of the size of the analysis, so overall we had 2,700 function nodes and 1,500 value nodes. As for promises, at the end of execution, about 4,100 of them remained unresolved or unrejected. They remained unsettled. About 209 of them were rejected, and 4,300 of them were fulfilled or resolved. So the first thing, in first glance, what you see here is that rejection is a valid status of a promise. So why are they not testing rejections? This is such a small number compared to the total number of promises that were being used. And in tests, you want to cover these cases, and especially if there are exceptions involved, you want to take that into account. So our first finding was that there's still a long way to go in terms of providing robust asynchronous programs that use promises. We looked into applications. About half of them had 0 to minimal rejected promises in their test cases. While in testing, you want to support a wide variety of inputs and execution paths. And we'll get back to this later in point. So this was one of our first findings that we did not even expect. So let's see some of the anti-patterns that we found. So I'm not going to go into detail for all of this. But basically, what they do, unsettled promises at the end, unnecessary promises, multiple attempts to settle a promise, the least they're doing is that they're cluttering your execution. So understanding asynchronous code is challenging as it is. Imagine just adding to the complexity for no good reason. So this is the at least technical debt that you're having, even if you're not having errors. But one other thing is that, for example, there's no justification for trying to settle a promise multiple times because it has no effect. It doesn't cause an error because it's JavaScript and you can do anything. But basically, it won't change anything. So when we see that, we suspect that it's not what the developers meant to do. There's maybe a flaw in their logic. There are cases that they did not expect. So the list they're telling us is that, OK, here are points of interest that we might want to look at. But these are actually a lot of things to look at. So we calculated the number of unique static locations that these were arising from. And they're actually manageable numbers. So all of these are coming from only a few places in each application. So the second category of the anti-patterns that I want to discuss, we felt had more impact in terms that they could lead into more serious issues. And we saw real examples of this, and they're included in the paper, that there are a ton of GitHub issues, and we found issues for actually all of these in our evaluation. And they could lead to errors, and they did in our evaluation and real work. So unreachable reaction, missing reject reaction, which we've been seeing from the beginning, and broken chains of promises. So what we did here, because we wanted to put more focus on these, we thought that, OK, these numbers are a bit high, so let's try to remove some false positives. So we applied some heuristics to kind of remove benign warnings. And we were able to do so. So just to, for example, go back to our ongoing example on missing reject reactions. So if you're missing a reject reaction, but down the chain of promises, there's another promise that you're somehow related to, and your exception can be captured there, we consider that a false warning because at least the exception will be visible. And we have a set of heuristics for all of them to remove some benign warnings to let developers focus more on what's more important to them. And after that, again, we calculate the static locations, and we find these locations for anti-patterns. But what do anti-patterns actually do? Do we really care? So we saw an example of this that I searched for an issue on GitHub and I found. But let's focus on that example and see what that means in terms of our evaluation. Did it have any serious implications? So we wanted to examine this case further. So we went back and checked, and we actually found that out of these promises that we're not expecting to be rejected, 7 of them were actually rejected. So this is not such a huge number, but these we found in a Node fetch module that has over 4 million weekly downloads. And we found these by running the tests. And if you remember from the beginning of the evaluation section, they weren't even really trying to test rejected promises. And this still happened, and these are errors. So when we talk about anti-patterns and they can affect that, we could find this just by running the test cases. And having the graphs, you can easily see that a promise is rejected, and the reject reaction is not attached, and the fulfill reaction is never executed. So you get the appropriate error messages that this is not supported and is rejected. And then you can see that how it can actually propagate down the chain of promises and reject every other promise on the way, and then die in silence because you won't even see the exception. That's why they're so hard to catch. OK, so as a final note, when we're actually looking at the applications and we're investigating the code, comparing them with the graphs, we saw that in a lot of places, quite a few places, developers were trying to come up with these band-aid solutions for these issues. So they weren't solving the problems, but they were like fixing it for that part. They were getting the exception and rethrowing it. They were manually rejecting all unsettled promises. So while these are by no means solutions, they show you that this is a real problem that they face in their normal everyday tasks, and that there is a need for systematic approaches that help them understand, fix, test, or debug these scenarios. So to wrap up, I talked about JavaScript promises and how they're helpful and how they can be challenging to use, and our approach for dynamically tracing these promises, inferring a model of their behavior, and then visualizing for our developers. And we showed how it can be actually useful in practice by finding at least bad coding practices that add to your technical debt and make your maintenance and comprehension more difficult, and in many cases, actual errors. And we showed that it actually performed with good performance, and it was practical. So with that, I want to conclude my talk. I'll also be available in the job market if you want to hire me. So thank you.
Thank you. First question.
So I wanted to ask about the promise graphs. Are they detailed enough, semantically detailed enough, that you could consider them to be a programming paradigm? Like, would you be able to write code that would be complete in the graph if you had a tool to do that?
Yes. So to give a bit more description, promise graphs were actually proposed in 2017 at OOPS Law by Magnus and Frank was here. So we got that concept, but that was not implemented, but it was a great start. So we got those. We actually designed programs to do that, and we implemented them, and we extended upon them. So there were some newer features. There were, for example, synchronization nodes that I didn't talk about. You can actually, you have ways of kind of synchronizing these that they can all get resolved, or they can race, or something that using those actually helps with some of these problems. So we added those features and we implemented them. And to answer you, yes, they, to a good extent, our tool is practical. And you're more than welcome to try it. And the artifact is also available with all our experimental data. So you can see how they worked.
Yeah, so I sort of had, I guess, an initial great talk. And I wanted to say, I was at 2 of the Node.js collaborator summits this year. And a big topic there is unhandled promise rejections, how to have developers understand asynchronous computation and failures much better. So I just want to say this is a really important problem. It's great people are looking at it. I also had a question on the fetch module bugs. Did you manage to PR those, and what's the status?
That's a great question. We did not. But it's a great idea, and we would like to give back to the community. And if you want to volunteer, all our results are available.
So I guess my question's related to that as well. I'm a bit skeptical of the unhandled promise rejections just being treated as bugs, or even saying that they might lead to bugs. The module that you used as an example was Node Fetch. You said it had many millions of downloads per week, and you saw that it also was using not only unhandled promise rejections, but unhandled promise rejections where the promise ended up being rejected. Did those lead to actual usable, like observable bugs? Did you look into those?
So that's the point. With JavaScript, so a lot of the stuff that happened in JavaScript would not compile, for example, with Java, right? But JavaScript runs, especially on the client side, unless you open the console and in the developer mode, look at the actual errors, you'll not see them for sure as a client. Even on the server side, this particular error goes unnoticed because you don't even see the exception. It just rejects the promise because I can manually throw a promise just to reject a promise. It might be something that I want to do as a developer. But then there's no way for me to distinguish that with from an exception that actually happened. And people do use exceptions to reject promises because they keep the stack trace. So it's actually very common to use those and pass them back. So this is the thing. They add a message, and they add a stack trace, and they return an exception. So how do I know that if I don't have support for that, was it intended, or is it an exception? But it will not show. If you just run it, it will show nothing. Your promise will be rejected, but promises can legally be rejected.
Any last question? Well, let's thank all the speakers.